All right, hello everyone. Section 10.9, the culmination of everything in the series chapter, and maybe, at least in terms of new material, my last video. So I hope you're as excited about that as I am. We do have more to do, don't worry, but I'm not sure how that's going to work in terms of videos and that sort of stuff. We'll figure that out as we go. So I need to give you one little definition that hasn't come up, and then we're going to do the last little section, which is I'm just really going to show you one example, actually. It's using a Taylor or Maclaurin series to approximate a function. So let's say you want to approximate, the natural log of 3, and we don't have a calculator, this or that. So we can use a power series to do that. But first of all, just a little definition. This is called an nth degree Taylor or Maclaurin polynomial. It basically just means this. So nth degree, we could hopefully remember from algebra what degree means, right? Degree means the highest power of x. So the nth degree Taylor just stops at the nth derivative or the nth power, because they're all the same thing, right? Because that x minus c to the nth over n factorial happens at the same time as the nth derivative. So all this says is this is just the definition of a Taylor series, right? F of c, f prime of c times x minus c. We just go until you get to the nth degree. So someone's going to say, find the 5th degree Taylor polynomial. All that means is take 5 derivatives. Stop when you get to the 5th degree. That's all that means. Or Maclaurin. If c equals 0, then it's a Maclaurin. Okay. So let me kind of just walk you through here. There's what we're going to do is we're going to use it. A Taylor series to approximate a function. And then we're also going to talk about how close that approximation is. That's kind of the important piece. So this is just the same thing we just did. Sorry, I don't know why I went to the other screen. This was the nth degree Taylor polynomial, of course. It turns out that when you use a certain amount of terms, like the n amount of terms or whatever it is, the error in that approximation. So if the more terms you use, the better your approximation will be. So if you're trying to approximate the natural log of 2.1, the more terms you use, the better it's going to be. But the error turns out to be at most equal to what's called the remainder. So the remainder of x, absolute value. So they're not really going to determine whether it's positive or negative. We just know how far off it is. And the remainder is basically the next term. Okay, so it's like the next term. So notice I went to the n plus first derivative, n plus first power, n plus 1 factorial. The only difference is I'm not going to put that c in for z. Okay, I'm going to put that I'm just going to put a z in there. Normally that would be a c, right? I'm just going to put this vague thing called z. And z is between c and x. Z is between c and x. And then what we're going to do is we're going to figure out what value of z between c and x makes this term as big as possible. And that's going to be my biggest possible error. It won't be the actual error. If it was the actual error, I know the answer, so that doesn't really make sense, but it will tell me how big the error possibly is. This is also called a Lagrange error estimate. We don't use this term in our book, but they use it on the AP test. So I want to introduce it to you right now. It'll be in some of our review later on also, but it's called the Lagrange error estimate. Okay, so tonight's homework, I'm just going to do one big example. It's going to say something like this. So first of all, it's going to be broken up into a couple parts. So they're going to start. So here's an example. This is actually number 9 in our book, but it's not one of the ones I assigned. So it's the square root of x, and they're going to say c equals 4, n equals 3, and it's going to say find the Taylor polynomial with remainder for the given c and the given n. And then that's going to be the first problem, the first set of problems that later on, they're going to ask you to use this exact same problem you did to approximate. So I'm going to do both. Okay. So the first thing we're going to do is find this Taylor polynomial with the remainder. So notice they've asked for n equals 3. That's 3 derivatives. However, remember the remainder is the next term. So I'm actually going to need 4 derivatives. So they're in essence asking for the third degree Taylor polynomial. But we need that next term because that's going to be the error. We're not going to generalize because they gave us a specific amount of terms. So if they give us a specific amount of terms, we don't have to try to generalize. So just kind of review the process here. N, so 0, 1, 2, 3. We are going to need to go to 4. This is going to be like the remainder. The function or the derivative. So the first one is root x. So I'm just going to call it x to the 1/2 if that's okay. The first derivative is 1/2 x to the negative 1/2. The second derivative, we drop the power, is negative 1/4 x to the negative 3/2. And the third derivative is positive 3/8 x to the negative 5/2. I do need to go one more. Okay, this will be the remainder. So one more is going to be negative 15 over 16 x to the negative 7/2. C is 4. C is 4, so that's what I'm going to plug in. So now I'm going to plug in 4 into the derivative or whatever, or function. So in this case, it's 2. Let's see, the square root of 4 for all these, the square root is going to be 2. And then we're going to have to power it with the 1/2, 5/2, 3/2, whatever. And then we're negative exponent is going to bring it to the bottom. So that's going to be 1/2 times 1/4. So I think that's going to be 1/8. The square root of 4 is 2. 2 cubed is 8. So that's going to be negative 1 over 32, I think. I hope I'm not making any mistakes here. We'll find out, I guess. The next one we square root of 4 is 2. 2 to the 5th is 32. That's going to be on the bottom. So it's going to be 3 over 32 times 8. Real quick, 32 times 8, 16, 20 over 2, 56. All right. On the remainder, remember, we don't put in that c. We put in what we're going to call z. Okay, we're going to put in z. So that's really easy. That's actually easier. Z to the negative 7/2. Now each one of these needs to get multiplied by x to the, not x to the n, but x, sorry. Oh gosh. X minus c to the n over n factorial. So this will be 2 times x minus 4. No, sorry. First one gets multiplied by 1, right? So that's just 2 times x minus c to the 0 over 0 factorial times 1. This one gets multiplied by just an x minus 4. This one gets multiplied by an x minus 4 squared over 2, or 2 factorial. This one gets multiplied by x minus 4 cubed over 3 factorial, or 6. We'll simplify that in a second. And then this one gets multiplied by x minus 4 to the 4th over 4 factorial. So if I just write it all out, the square root of x equals, the first term is 2 plus 1/8 times x minus 4 minus x minus 4 squared over 64, 32 times 2, plus, I could reduce here, that 3 and the 6 is a 2, so it's going to be 512, right? X minus 4 cubed over 512 plus 15/16. And the remainder, it doesn't matter whether it's positive or negative. So it's 15/16 z to the negative 7/2 times x minus 4 to the 4th over 4 factorial. I guess I should do that. Sorry. 4 factorial is 4 times 3 is 24. So real quick, I'm just using my calculator sheet. 16 times 24 is 384. So let's just put this over 384. Where z is between, whoops, sorry about that. Where z is between c and x. So for my particular case, c is 4. And we don't have an x yet. X is when we're going to approximate it, which we're about to do, because the next question that would come would be use this to evaluate the square root of 4.03. Okay, use this to evaluate the 4.03 and find what's called the error estimate. So all that means is I'm plugging 4.03 in for x. It would be a calculator problem at this point, or just leave it alone. So the square root of 4.03 would be equal to 2 plus 1/8 times 0.03 minus 0.03 squared over 64 plus 0.03 cubed over 512. Air is 15 z. I'm going to rewrite this again for you here. Z times 0.03 to the fourth over 384. And here's the thing, right? Z is between C and X, 4 and 4.03. Right, so now what we need to do to find this error. So by the way, we would just take out our calculators and punch and chug on that one. That would be our approximation. The error, same thing. However, we got to plug in a number for Z. So the idea here is that we want to make this error as big as possible. It's like the worst case scenario. So just remember here that this Z is actually down in the bottom as a 7/2, right? So if we want to make this error as big as possible, we need to make Z as small as possible, right? The smaller the Z is, the bigger that number will be. So that's going to be 4. So the error is going to be 15 times 0.03 to the fourth. Oh, this is called an error estimate. Over 384 times 4 to the 7/2, whatever that is. Just dump that on our calculator, and that would be our error. Okay. So you're going to see 4 or 5 problems like this. You have to do the first setup, then you've got to use it to approximate. Find the error. It's the next term, and you make the next term as big as possible. One thing to notice, or not notice it, but to tell you, if the series is alternating, okay, the biggest the error will ever be is the next term, regardless of the C and X and all that. You just would plug in like you normally would. You just continue to find the terms. So in other words, if we have, let's just do a little simple one, 2 minus 1 plus 1/2 minus 1/4 plus 1/8, so on. If I said, find the sum after that many terms, what's the error? It's always that term if it's alternating. That's the biggest the error can possibly be, is that next term. So if it's an alternating series, you don't have to go through this process of the Z and the X. Notice what we did was not alternating. It was close, but it wasn't alternating at the beginning, right? Plus, plus, and then we had some alternating. So some will alternate, some won't. If they don't alternate, we do this process we just did. If they do alternate, then the error is always the next term. We'll talk in class a little bit about why that's true. I think I may have mentioned that somewhere along the line, but I'm not sure. So anyway, congratulations. You just made it through Calculus BC. We'll do some more, though, of course, with a little bit of review. And we'll go over these problems in class.